of what? A atom. So that means a new bond is, for example, when HA and what happened HB, they're forming bonding like this. Attractive force are generating between what happened? Electron of the nucleus of A. Right? Similarly, attractive force are generating. Similarly, what happened? Electron of A and nucleus of what? B. Attraction force are taking. So this is actually leading to form actually chemical bond. Now let me see in this case, this is not required for you in examination. Nobody asks this type of things actually. We will go to what directly? Overlapping. Let me see now. So how many types of overlappings will be there? Isn't it? How many types of overlappings will be there? Now for example, first overlapping will be SS overlapping. I'm drawing here over here, you see here. S orbital always will be spherical in nature, right? They are spherical in nature. S orbital. If it is having an electron, and this is having what? Downward side electron. Now both will overlap like this. And the two electrons we can place over here. This is what sigma SS overlapping. Because if the bond is formed here, what happened? Sigma bond SS overlap. Right? Now next, if you observe what happened, p orbital. I am taking what happened here, p orbital. In the p orbital, what happens here? I have taken p orbital shape. Anybody? What is the shape of p orbital beta?
Double shape.
One is having, see, the charges actually it is positive, negative is a wave function charges beta. Simply there are signs only. I have taken negative sign, positive sign. Here also positive sign, negative sign. So when they overlap, what happened? Same will be overlap here. Same, it is not charge beta. It is not at all charge. It is a sign only. Same sign will overlap. Now why this is same sign? I will explain by taking this example beta. You will get one doubt actually. So I will explain this one by taking this example. For example, if a wave is propagating like this, correct? This a wave is propagating like this. Now this is, I am saying positive sign. I have taken one more wave also. I have taken one more wave also. Now this is a negative sign. Sorry, this one I will take downward direction. Sorry. In the downward, I am saying downward like this. This is a wave is propagating like this. So first wave is propagating in this manner, a second wave is propagating in this manner like this. Now it is plus and minus. When they meet each other, what happens here? Both will be cancelled with each other. We don't get any wave. No wave is produced. So plus minus, if they interact, what happen? Both will be cancelled. We get a no wave. We don't get any wave actually. Right? Now, understood this one?
Yes, sir.
This is called what? Destructive interference. You just this one you will get in the physics section. This is called what? Destructive interference. Now I'll take what? Constructive interference like this. A constructive interference. Again plus and plus. Now definitely they will meet with each other to give what happened like this. To give an intensified wave like this. The wave intensity what happened? Increased here. Because plus and plus what happened? Plus 5 what happened? 10 we get. 5 rupees if you add what happened? 10 rupees we get. Similarly what happened? This is what? Same what happened? Signs they meet with each other. Which type of interference will be formed here? Constructive interference. In the previous case, what we discussed? Destructive here. Now it is constructive interference. You can take even minus also. Minus also you can take. Same thing you can take. Now you observe what happened. PZ orbital. Same signs are overlapping. They are not charges beta, they are signs. Same signs are overlapping. So this is getting what? Positive overlap. Now you observe what happened. Different signs are overlapping. This is called what? Negative overlap. This is called in phase and this one is called out phase. Now overlapping can take place between p and s orbital also. You observe p and s orbital also. So in this case we are getting what type of? We are getting sigma Pz and Pz we are getting. Sigma Pz, Pz we are getting. In this case, sigma bond, sp bond we are going to get. sp overlap. S orbital and p orbital overlap is taking place. Now this is what actually positive because same signs are overlapping. Opposite are overlapping. Destructive interference, negative overlapping. Generally, it will not take place. You observe here. Now here, see, pz orbital is I am taking along the axis, and px and py will take isn't like this actually because they will form pi bonds, so we can take like this. Here also what happened? Constructive interference or positive overlapping, destructive interference or negative overlapping, and py if I take what happened? Again constructive, positive overlapping, destructive, negative overlapping. One more overlapping will be there, that is called zero overlap. We have to overlap, isn't it? Either in this manner or in this manner. But in this case, what happened? Both plus, 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 minus. Now, this is called what? Zero overlap. This is not correct. Actually. Plus, 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 minus. So, it is not at all called overlap. This is called zero overlap. Because of the different orientation. Now, here it is not at all, it is overlapping. So, these are zero overlaps, we call this. These are what? Zero overlaps. So, this is about the overlapping. So, I don't think this, you may don't get any questions from this one. Just overlapping is how they takes place. Actually. Right? Now, we get a question now here. Now, if I take what happened, CH bonds in methane, they are, why they are not oriented 90 degrees here? Actually, when you observe what happened, they are having 109 degrees here. The bond angle if you observe. Water, if you observe what happened, 109 degrees were happening. 104 degrees, sorry. Water, if you observe what happened, 104 degrees here happening. Now, if you observe methane, what happened? If you observe methane, what happened? This is the structure of methane. Now, if I take like this, the bond angle will be 90 degrees. This one. But actually, what is the bond angle? 109 degrees. What is the reason? The structure of methane looks what happened? Tetrahedral like this. It looks what happened? Tetrahedral like this. Now, in this case, what happened? The bond angle will be 109 degrees, more than 90 degrees. Now, this thing, isn't it, does not explain by the previous theories here, isn't it? So, whatever we are discussing is not fit with what? Tetrahedral. So, here what happened? Even in ammonia also. Ammonia, if you observe what happened? NH, NH, NH. What is the bond angle here? 90 degrees. But actual structure is what? Like this. The bond angle will be 104 degrees. Now, why ammonia is having 107 degrees? Sorry, 107 degrees. Why ammonia is having 107 degrees here? That why not it 90 degrees? This we are explaining now here by using what actually what? This hybridization theories. Before hybridization, what happened? S orbital overlaps. We get like this. Sigma SS bond will be formed. SP overlapping. One S orbital, P orbital is dumbbell shape. We are going to get sigma SP overlap. Now PP overlapping like this. In this case, sigma PX and PX like this. And finally, what happened? Pi orbital. Pi orbital always will get sideways like this. These two will overlap like this. Generally, it may be PX or PY and PY. PZ will be along the axis here. It will form sigma bond actually. PZ will form sigma bond. PZ will form sigma bond. Whereas PX and PY will form generally what happened? Pi bonds actually. This is the pi bond actually. So this is a simple things how the overlapping takes place between the S orbital and P orbitals. Very simple. Now important thing is we move to what? Hybridization. We will get questions from hybridization topic in examinations. Now, what is the hybridization? What is the meaning of hybridization? So, before hybridization, let me see what happened. Every atom will have atomic orbitals, right? Every atom will have atomic orbitals. S orbital, P orbital, they are atomic orbitals. Now, these atomic orbitals are pure atomic orbitals. Once these are mixed, okay? When the pure atomic orbitals are mixed, we are going to get a new orbitals. They are called what? Hybrid orbitals. This process is called what? Hybridization. Okay. For example, I'm taking what? One s orbital. One s orbital. And what happened? Three p orbitals are mixed. In that case, we are going to get what? A hybrid orbitals like this. A hybrid orbital like this. Now this is called what? Hybrid orbital. How you got hybrid orbital beta? How you got hybrid orbital? When pure atomic orbitals, isn't it, mix together, merge with each other to give what here? Hybrid orbitals. Now, what are the conditions for this one? What are the conditions for this formation of hybrid orbitals? Isn't it? Now, for example, first thing if you observe here, what are the features? For example, if one s orbital and three p orbitals are participating in the hybridization, now how many hybrid orbitals will get? 4. That means the number of atomic orbitals will always equal to number of hybrid orbitals. You observe here what happened? How many I have taken? 1s, 1, 3 p orbital. Now how many hybrid orbitals we got? 1, 2, 3, 4. I got 4 hybrid orbitals. For example, if I mix one s orbital and 2 p orbitals, I'm mixing what? 2 p orbitals. In that case, I'm going to get 3 hybrid orbitals like this. 3 hybrid orbitals like this. 1, 2, 3. That means the number of hybrid orbitals is always equal to number of atomic orbitals. Next. Now, when they are mixing with each other, no, these should be what? Similar energy. They both should have what? Similar energy. That means what happened when you are overlapping, what happened? You can't overlap 1s and what happened? Something what happened for 3D, 5D like this. So at least they should have what? Similar energy. Next, third one, if you observe what happened, hybrid orbitals are more effective in forming stable bonds when you compare to pure orbital. That means simple s orbital if you take it. You have taken what? Simple s orbital. They are actually very less effective. You see what happened? S and S overlap. S and P is overlapping. S and P is overlapping. They're actually simple pure atomic orbital. This is very less effective. When you take what happened, hybrid orbitals, they're what? More effective. That means hybridization will give more overlapping, strong overlapping, will form stable bonds, isn't it? Comparing with what? Atomic orbitals. Next, if you observe what happened, how this is forming, why this shape is forming. When you observe this one, in this what happened, in space, in this, there will be minimum repulsions present between the electron pairs. So that what happened, we get a stable arrangement, and this leads to what? A geometry. This leads to a geometry. See, why water is having what? Angular shape. Angular shape because of oxygen central atom. Because of what actually? Hybridization. Let me discuss in later. Everything we'll discuss in detail. Now, next important points, if you observe what happened, the orbitals present in the valence shell of the atom are hybrid. That means what happened? Which orbitals will involve in the hybridization? If the ask question, which orbitals are involving beta? Valency shell orbitals, last shell orbitals will involve in the hybridization. For example, if I take what happened, fluorine configuration will be 1s2, 2s2, 2p5. Now, which will involve in the hybridization? Last shell, not the inner shell actually. The orbitals undergoing hybridization should have almost equal energy. Same thing. They should have same energy. No? Whichever the orbitals are undergoing. Now these two will have same energy only. No? Now these two are undergoing what? Mixing to each other. So they will have definitely what happened? Similar energy. Now promotion of electron is not essential condition prior to hybridization. If you want to do the hybridization, no need to excite the electron. Directly we can do this. Without any excitation of electron, we can do this. If we do example, we get all these things. It is not necessary that only half-filled orbitals participate in the hybridization. In some case, even filled, isn't it? In the last case, in the last class, I told you, no, only unpaired electrons are participating in bond. But here, even lone pair also will participate in the bonding. Even lone pair. In the previous last class, we have taken only bond pairs are participating in the bonding. Now, the filled orbitals are also will participate in the bonding. That means in the hybridization, I need to say. Now let me see now sp and sp2 and sp3 hybridization. Now I will explain what sp, sp2, sp3 in PPT. I will explain this one. sp3, dsp3, everything we'll see now, right? We'll take in PPT like this. Is it visible for you, beta?
Yes, sir.
Yes, sir.
So the features. So these are the different types are there: SP, SP2, SP3, SP3D, SP3D2, SP3D3. But we'll discuss up to what happened SP3D2 according to our syllabus. First of all, we'll see what SP hybridization. We'll see what SP hybridization. In SP hybridization, how many S orbitals will be there, beta? How many S orbitals will be there here? How many P orbitals will be there, beta?
One.
One.
P orbital. Now, how many hybrid orbitals will get?
Sir, 2.
Two hybrid orbitals will get. Okay, right. Next. And what will be the shape? Means linear shape. Bond angle will be 180 degrees. Number of sigma bonds will be 2. Percentage of S will be 50. Percentage of P 50. It is okay for you. Okay. Now let me see these how it is. With what? Overlapping. Now this is S orbital. Everyone is visible now. This one S orbital, right? Now
Yes, sir.
what actually P orbital, and not reacting, merging it is mixing P orbital. Both are what happen? Merging or mixing to give what now here? Hybrid orbital. Now the hybrid orbital will like this. These are the two. One first order hybrid orbital. Second, understood better, all of you. When S orbital and P orbital are mixing together, right? We got two hybrid orbital. Number one, number two hybrid orbital. Now these two will arrange in which they get less repulsions. So how they arrange here? Linear shape. Like this they will arrange. So in this case, these two are getting less repulsions. Understood how sp hybrid orbital is formed?
Yes, sir.
Right? So this is the, definitely it is a straight line, therefore linear shape. Definitely linear shape. The bond angle will be 180 degrees, isn't it? sp hybrid orbital. Now, if you observe what happened, this is having small lobe, we can call this one. This is small lobe, we can call this one. This part is small lobe. This part is what? Big lobe. Now, why they are taken like this, you see? This is the pure atomic orbital. This is a pure atomic orbital. How do you distinguish between these two? If you have pure atomic orbitals, will have only what? Large lobes only. Only large lobes there are. But hybrid orbitals will have small lobe and big lobe. Both they are having actually. Large lobe and small lobe. Both they are actually having. Then smaller one. In this way, we can easily identify what? Hybrid and pure atomic orbitals. Right? I will take one example here. Beryllium chloride will form sp hybridization. The bond angle of beryllium chloride will be 180 degrees. Now I have to explain this one, how beryllium is forming sp hybridization. This is very, very important beta. You have to observe here. Watch carefully video here. First of all, I am taking what? Beryllium, which you have to take central atom beta. First of all, you have to take what? Central atom. What is that one? Beryllium is the central atom. Okay. Now select the beryllium. Now what is the ground state electronic configuration beta? 1s2, 2s2. The ground state electronic configuration of beryllium is 1s2 and 2s2. Now it will be 2p orbital also will be there. No. This is 1s2. This is a 2s2. There will be 2p orbital also there, but we don't have any electrons inside this. Now, just now I told you which electrons will involve in the hybridization beta? Only valence shell orbitals only involved, not inner shell. So don't involve this one, because inner shell involve only what happened here? Valence shell. Now here, what we'll do here? Excite this electron over here like this. Excite this electron like this. That means what happened? You do one thing. This electron will jump into this one. So what happened? Now this is s orbital. This one is what here? P orbital. P orbital. Now next, what happening here? Now one s orbital from here and one p orbital from here, both are actually what? Overlapping like this. So one 2s orbital, isn't it? This one. One 2s orbital, this one. And one 2p orbital. So they don't involve in the hybridization. So they are mixing like this. One 2s orbital, one 2 orbital will mix to give two sp hybrid orbitals. Right? Now, the two sp hybrid orbitals oriented in opposite direction or not, you see? See, they are oriented in opposite direction or you see? Like this. In this way. In this way they are oriented. One is like this. One is like this. Other is what happened. Second one is like, both are in opposite direction here, right? Now, once if you get what, I will explain this one here. Now, after this, what we got like this. No? One is like this. They are oriented in opposite direction. Like after this, what happened? After formation of this, what happened? How many chlorine atoms are there? About 2 chlorine atoms are there. Now, what is the electronic configuration of chlorine? Neon configuration. Next, what happened? 3s2, 3p5. Now, 3s2, 3p5, we can write like this. 3s2, this one. 3p5, like this. Now, this orbital, which I am calling as pz orbital, isn't it? Will now overlap. How many chlorines are there? 2 chlorines are there? No. Now, each chlorine atom with pz orbital will overlap like this. Each chlorine atom will overlap like this. This is the pz orbital of what? Chlorine. This one is also what? Pz orbital of chlorine. This one. Pz orbital of chlorine. Next, this is what actually sp hybrid orbital. This one is what? sp hybrid orbital. Now, both are having single electron. No, put here what? Single electrons like this. Both you are having electrons. Now, you get a sigma bond with what? sp and pz orbital of chlorine. Here also you got a sigma bond, sp and pz orbital. How many sigma bonds you got beta here? 2 sigma bonds. In the first case, what we discussed, you observe. What we discussed here? Here. How many sigma bonds we got in the first? You discussed this one. 2 sigma bonds we got. So we got 2 sigma bonds only, no, here. This is about what? Formation of barium chloride. Which hybridization it is having? sp hybridization it is having. With what? 2 sigma bonds like this. Here it is sigma, sp, pz orbital or p, you can write simply. Sigma, can take some other examples, C2H2, PF2, CO2, zinc, all these are examples for our actually sp hybridizations only. Now, formation of C2H2 we will discuss separately after the hybridization. Next, it is already you know which percentage beta? Percentage of scatter, how much beta?
50.
50%, right? The bond angle in sp hybridization beta?
180.
180 degrees.
180 degrees.
Right. I will move to what? sp2 hybridization. See, now in this case, one s orbital and 2 p orbitals. Now, total how many we get? 3 hybrid orbitals we get. 3 sp2 hybrid orbitals we get. Like this. So now I am taking what actually one s orbital. In the axis I have taken one s orbital. And how many p orbitals I have taken? 2 p orbitals I have taken. One is here. Now we got like one sp2 first sp2 orbital, second sp2 hybrid orbital, third sp2 hybrid orbital. Now they are arranged. Actually, there are 3 hybrid orbitals we got. Now these 3 will arrange in this manner, trigonal planar shape. They are arranged in the form of trigonal planar. So for this one, bond angle will be what here? 120 degrees. It will be 120 degrees. So one s orbital, 2 p orbitals are mixing to give 3 equivalent means same energy of sp2 hybrid orbitals. Right? Take an example, bf3. We are taking an example, bf3. One boron is what? Central atom, and 3 fluorines are surrounding atoms. Now let me see this one. First of all, boron. Now let me see fluorine, no problem. And boron is having, fluorine is having single electron because 1s2, 2s2, 2p2, 2px2, 2py2, 2pz1. This is the thing. Okay, leave it this one. Next, go for what? Boron. 1s2, 2s2, 2p1. Now what you do? Exert this electron over here. Put this electron over here like this. Now what we get here? Exerted configuration. One s orbital and 2 p orbitals are now will involving in the hybridization. Now what we get here? A hybrid orbital we get. sp2 hybrid orbital we get like this. sp2 hybrid orbital we get like this. Now this sp2 hybrid orbital now will overlap with what? P orbital of fluorine. Now where we got p orbital of fluorine beta? So I'm explaining this one. Again, I'm taking fluorine configuration, helium configuration, 2s2, 2p5. 2s2 completely filled, no overlapping. 2p5, we can write like this, 2p5. Now this is what? Unpaired electron. That pz orbital is unpaired electron. This orbital will now overlap. You can also write like this, hybrid orbital, okay, hybrid orbital and hybrid orbital. Now this pz orbital, how many fluorines are there? 3 fluorines are there. So 3 pz orbitals will overlap like this. 3 pz orbitals will overlap. Now here what type of bond is formed? Sigma bond between what? sp2 hybrid orbital and pz orbital of what? This is from fluorine. This is from what? Boron. Similarly here also what? Sigma sp2 pz orbital. Sigma sp2 pz orbital. So how many sigma bonds are found here? 3 sigma bonds are found with sp2 and pz orbital. Now the bond angle will be 120 degrees here, right? The bond angle will be 120 degrees and the shape is called trigonal planar here. The shape will be trigonal planar. The percentage of S character will be 1/3. 1/3 is equal to 33%. Isn't it? Sigma bonds are how many? 3. Pi bonds will be 0. And type of overlapping will be sp2p overlapping. Other examples you can take. These are the other examples. C2H4, C6H6, all the other examples here. And formation of C2H4 I will discuss after the hybridization. Percentage of P kitna beta? sp2 hybridization?
66.67.
Remaining 33 will be 66.67%. What type of overlapping is involved in this one?
C, option C.
sp2p overlapping. C2H4 definitely will be how? Same, sp2p overlapping. sp2 hybridization overlap. I will explain this one after. Both C2H2 and C2H4. Bond angle will be?
So 120.
120.
120.
120.
Right. Next. sp3 hybridization. Let me see. sp3 hybridization. Now here one s orbital, 3 p orbitals will undergo mixing or merging to give 4 equivalent sp3 hybrid orbitals. And the shape will be what here? Tetrahedral shape. Isn't it? Now let me see that one s orbital and first p orbital, second p orbital, third p orbital. So the 3 p orbitals are now mixing with each other and we are getting how many hybrid orbitals? First one, second one, third one. we got 4 hybrid orbitals. Now these will make a shape in the space in which they will get less repulsion. So when you have 4 hybrid orbitals, they will gain a tetrahedral shape like this. They will gain a tetrahedral shape like this. This is called what? A tetrahedral geometry, we can call this one, right? Example, we can take what? sp3 hybridization. I'm taking what? You can take a CH4 also, we can take. Here we can take ammonia also, I can take. Ammonia if they taken what? The ground state configuration will be what? 1s2, 2s2, 2p3, like this. Okay. Now 1s orbital. I told you no, even lone pair also involved in the hybridization. In the important points, postulates, we have seen this one. Silent features we have seen. Lone pair can involve, or even for bond, that means single electrons also can be involved in the overlapping. 1s orbital, 3 p orbitals are overlapping here. Therefore, isn't it? They're going to get like this. This way it will be looks. So I will take best example. First of all, we'll discuss ammonia. Shall we take what happened? Methane. Better take what methane here. We'll see methane here, sp3 hybridization. Later we'll take what? Ammonia and water. We'll take methane, later we'll take what? Remaining one. Now I am taking sp3 example, methane, CH4 I am taking. The central atom is what? Carbon. Carbon configuration will be helium configuration, 2s2, 2p2. 2s2 means we can write the 2 electrons like this here. Like this you can write. After this, what happened? You jump this electron over here because empty orbital is there. You jump like this. You will get like this. Now 1 s orbital and 3 p orbitals here. 3 p orbitals. They mix together to form what actually? A tetrahedral geometry like this. 1, 2, 3, 4. This is a tetrahedral geometry. Is sp3 hybrid orbital? sp3 is also sp3. Again, what happened? sp3. Now, how many hydrogens are there here? 4 hydrogens. Hydrogen configuration is what? 1s1 configuration. 1s means what happened? This is the thing. Now, here sp3 will overlap with s orbital of what? Hydrogen. S orbital of hydrogen. Again, also what? S orbital of hydrogen. Here also s orbital of hydrogen. Here also what happened? S orbital of hydrogen. So what type of bond will get? Sigma sp3, yes. Here also sigma sp3, yes. Sigma sp3, yes. Here also what happened? Sigma sp3, yes. So here how many sigma bonds we are getting better? 4 sigma with sp3 and s overlap. Okay, the bond angle will be here what? 1 regular bond angle 109 degrees 20 something what minutes like that. 109 degrees you can take roughly. So we can take example what? CH4 we can take, even ammonia also we can take, even water also we can take, but they are having a lone pairs in that one. They are having a lone pairs in that one. We see that one also. Now you observe here what happened, what we discussed. Let me see again here. Now we completed the sp hybridization, right? Example we taken beryllium chloride. We got this type of things actually. And we completed sp2 hybridization. Example we have taken for sp2 boron trichloride, BCl3. This BCl3 we have taken. And finally we have taken sp3 hybridization. We have taken sp3 hybridization. And example you have taken what here? Methane molecule, CH4 molecule I have taken. This is the methane molecule you have taken. Like this, isn't it? Now let me take water and ammonia also. Now let me take here water and ammonia also let me. These are also having sp3 hybridization. But now what is shape of methane beta? What shape we got here? What bond angle we got here?
109.
Tetrahedral shape.
Tetrahedral shape. That means when you have sp3 hybridization, the shape will be tetrahedral and
90 degrees.
109 degrees. Now what happens to the ammonia and water? Ammonia and water also will form sp3 hybridization. They also forming sp3 hybridization. But their bond angles, if you observe what happened, they decreased to ammonia is 107, water is 104. And the shape also not tetrahedron, it is pyramidal shape, and water is what? Angular shape. So that is because of what? Lone pairs. Isn't it? That is because of what? Lone pairs are present. Because of the lone pairs, what happened? Repulsions are generated here. See, lone pair are present here. Repulsions are generating here. Because of this repulsion, lone pair, bond pair repulsions and lone pair repulsions, the bond angle is decreased from, isn't it? 107 degrees for what? Ammonia, isn't it? From what? 109 degrees. Similarly, in water, you are having in this case lone pair and lone pair repulsions are there. And lone pair, bond pair repulsions are there. Now bond angle is decreased some 104 degrees and shape is converting into V shape or angular shape or bent shape, we can call this. And I will show how it is taking place in a PPT like this. Let me see this one. Here. So I'm taking ammonia here. I'm taking ammonia NH3. Nitrogen configuration, if you observe what happened. Helium configuration. 2s2, 2p3. 2s2 we can write like this. 2p3 we have to write like this. Like this we have to write. Now of course, one s orbital and 3 p orbitals are mixing. When they mix, what happened? We are going to get what actually? 4 hybrid orbitals like this. 4 like this. We got 4 sp3. It is sp3. I will write outside. sp3 hybrid orbital. sp3 hybrid orbital. sp3 hybrid orbital. Now in this case, it will overlap with 3 hydrogens here. So here you are having lone pair. This one, 2 electrons. Here you are having single electron. Write down single electron. Write down single electron. Write down single electron. These are having single electrons. Now it is overlapping with hydrogen like this. Hydrogen. 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 Now hydrogen also having what? 1 electron. 1s1 configuration, but 1 electron I am writing like this. Hydrogen electrons I am writing like this. This is for hydrogen. Hydrogen. Now this we can write like this. H. 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 So here we got what sigma bond we got here? sp3 yes sigma bond. sp3 yes sigma bond. sp3 yes sigma bond. This is sp3 sigma. Which bond it is actually? Sigma sp3 yes bond. This one is also sigma sp3 yes. This one is a sigma sp3. Now write down the lone pair over here. This is a lone pair. Now here what is happening? This lone pair is a hybrid orbital. It is also a hybrid orbital only, but not involving in any types of bonding. Now this lone pair will locate in the atom in which we get more repulsions. So lone pair and what happened? Bond pair repulsions will be there. Lone pair and bond pair repulsions will be there. Because of this, bond angle is what? Changing to 109 to 107 degrees. The shape also what? We can't consider this one. Now shape you have to consider only this one. Now this shape looks what happened? Pyramidal shape. Therefore they taken what? Trigonal pyramidal shape. Now if you observe for what? Water. If you observe for water, water is having what? Again helium configuration 2s2, 2p4 here. Now 2s2, 2 electrons in oxygen like this and 4 electrons in like this. These are 4 electrons having like this. Now these two are the lone pairs and these are having unpaired. Now 1 s orbital and 3 p orbitals will mix here, okay, to give again what? Hybrid orbitals like this. 1. Next what happened? 2, 3, 4. So you're having a lone pair here, and you're also having a lone pair here, right? Now here you're having unpaired electron. Please wait a bit. One electron here, one electron is here like this, right? Now how many hydrogens are there? 2 hydrogens are there. Now you take what hydrogen, you also what hydrogen. And hydrogen has 1s1 configuration. Put this electron over here. Put this electron over. Then this bond is called what? Again, sp3. Yes. This one is also what? sp3s. Now, if you observe what happens, same like ammonia, we are getting a shape like this. Now, oxygen, hydrogen, hydrogen. This is sigma sp3s orbital, sigma sp3s, lone pairs here, lone pairs here. We got 2 lone pairs with hybrid orbitals. So here what type of repulsions will be there? Lone pair, and lone pair, bond pair. Obviously what happened? Bond pair and bond pair. 3 types of repulsions are there here. Now that is the reason bond angle from 109 degrees converting into 104 degrees. And the shape also will change it into P shape. So this is about the ammonia. Now in VBT we got one question. No, in ammonia the bond angle should be 90 degrees. Why it is having 107 degrees? Because of the repulsions. Similar in water, the bond angle should be 90 degrees, but you are having how much here? 104 degrees because of the lone pair repulsions. Yes. Just a minute. Okay, this is about what actually? Hybridization. Understood hybridization better?
Yes, sir.
Everything. So how many types we completed now?
Yes, sir.
SP2, SP3 and SP hybridization we completed. Tomorrow class will take formation of what? Sigma and pi bond. How the sigma bond is formed in C2H4 and what? C2H2. Okay? C2H2 also. This one. We'll discuss tomorrow this topic. Actually. These 2 things. Right? If you have any doubts, you can ask me now. Yeah. Having any doubts?